All right, let's get started. I'm very pleased to welcome the team from Bytedance to give their talk on building unified large-scale data processing pipelines for multimodal models using Ray. Please join me in a warm welcome to Xiaohong, Zhibei, and Liguang.
Hello, everyone. It's so many people here. We are honored to be here to share our topic: building unified large-scale data processing pipelines for multimodal using Ray with my colleagues Zhibei and Liguang. In the beginning, before we start today's content, please allow me to give a brief background introduction. We are from Bytedance Seed and Data Info team. Our main responsibility is to build a high-performance scale and distributed data processing platform. We aim to enhance model performance through data-driven approach. Because we are dealing with three major challenges. First, we are faced an exponential growth in data volume, with each dataset reaching several petabytes. Second, we have limited GPU and CPU resources. Third, processing tasks are increasingly complex with multi-steps and sophisticated algorithms. Our main objective is to enhance efficiency and minimize resource consumption. Ray is the answer. It can handle large data volume, optimize heterogeneous resource allocation, and flexible orchestration capability, leverage recall, redata, and result. Let's delve into three key aspects: audio data processing, video data processing, and the underlying Ray info. I will share the first section, audio data processing. After briefly summarize the background, now let's dive into the detail of our data processing platform and how Ray helps us deal with the problem we mentioned earlier. The architecture of our data processing platform can be divided into three layers, just like you see from the slides. The first layer is the info layer. It plays a crucial role in managing and providing essential storage and computation resources. Additionally, it is responsible for task scheduling, ensure efficient utilization, available resources, and smooth execution, and OS process. The second layer is the self-developed data pipeline layer, which is specially crafted to handle the complex data flow and the performance of a series of data transformation and process tasks. The top layer is the application layer. The top layer is the application layer, where the process data is utilized to power various large speech models, such like music generation. And we have a demo after this slide. Let's zoom in the pipeline layer, how we orchestrate the data processing pipeline. The first concept is node. What is named node? It typically presents a specific task or operator, such as the filter operator, annotation operator, or deduper operator. Some nodes need CPU resources, and some other need GPU resources. The second concept is flow. Flow is defined as a data or control transfer relationship between nodes, and is a direction connection. A node can have multiple input flows or output flows. Our DAG is defined by node and flow and assembled through YAML, so it's efficient for us. We have redefined a series of common pipelines. By resembling these common pipelines, we can meet the data requirement for model training. This approach greatly improves our work efficiency and provides a more flexibility solution for data processing and model training. So there is a diagram of all the pipelines, so it's the common pipelines. During the initialized implementation, we encountered 4 main issues that slow the project progress. The first issue is high scalability. They are difficult to handle large-scale data due to efficient resource utilization. Moreover, they are challenging in scale from a single node to multiple nodes, so it's a difficult work for us at first. The second issue is task scheduling and loading balancing. The complexity of manually managed task allocation has increased, leading to an unreasonable task distribution and affect the execution efficiency of the project. The third issue is high available and fault tolerance. You know, the AI scenario is very difficult and the model is so complex. It's a lack of automatic mechanism for task retries and node for failure detection. As a result, during node interruption, there may be task failure and data loss. The last issue is data transfer and sharing need to manually implement efficient data transfer and synchronization among task and node. Performance bottleneck occur and node complexity increase. After integration, investigating Ray, we start using Ray core capability. Why can we quickly transformation to Ray solution is also leverage Ray is Python friendly. And it's not so hard for us to transform the solution to Ray. Recall prime robust distributed compute capability, however, only depend on recall. We still face some issues. You can imagine you just have the distribution computing capability, but the data still shows to cover by yourself. So the first issue is data distribution and the sharding management. It requires manual management of data sharding and distribution, which not only increase compatibility, but also increase the risk of imbalance. The second issue is problem of how data reading and loading. It's lack efficient automatic data reading and loading mechanism, which is likely to affect overall efficiency. The last issue is lack of high-level data operation functions. So we should to cost so many time to deployment to the functionality. So read data is apply as the high-level data operation is manually implement and can give us common data operators. It's increase the maintenance cost. To conclude my part, you can imagine the other things. If someone wants to use the unionized model, how you solve for the others? If we just with recall read data, we still have other things to make the model as a service. So the other things is resolve. It can help us something. The first one is complexity to model implement, and the second one is give us stable service. On the one hand, for efficient model deployment and service, resolve provide easy APIs and enable model to be quickly transferred into access service. It means we can push our model efficiently and make it run faster and faster. If we have enough data and the model can have more performance, so it's just named the scaling law. On the other hand, in terms of high available and fault tolerance, Resolve have built-in high available and fault tolerance machines and can automatically detect and recover from the faulty node and ensure stable of the service. So it's very important for our scenarios. If you manage so many pods and you should scale up your data processing efficiency, so the stable is very, very important. There are also a draft of our pipeline, and there is a data block, and we just use the read data to get a map step. I also drafted one page for after we use a array. So it's time pass to my colleague Zhibei.
Thank you, Xiaohong, for the comprehensive introduction to audio data processing by using Ray. This is Zhibei from the Video Generation Foundation Model team in Bytedance. In the next few minutes, I will use an example to demonstrate how we use Ray to empower our video data processing pipeline. To begin with, let me introduce the background and the problem. So our team is building a video generation foundation models. Everybody knows the high volume and high quality video data is the key for the model training. However, video data is quite large compared with like a text, image, and audio. And also, video data takes more computation resource and takes more time compared with the other data formats. So for example, like for videos, most of the common operation will be like using FMPEG to do video encoding and decoding. It takes some time, yeah. So for us, efficient processing of vast amount of video data to achieve high throughput and also scalability is a key challenge for us. So let me walk you through an overview of our video data processing pipeline. Basically, I have 3 steps. So first, we have like a list of raw videos. The raw videos can be several seconds to be several hours. The next step, we will have a video splitter algorithm, which will split the videos into different clips. And each clip can be several seconds, maybe to 1 minute something. And then, next step, we have the video processing algorithm. It has 2 things to do. First, crop the videos. So we only select the videos we want, and also we will score the videos. For example, we run some like motion processors, we run some quality processors to give the scores for these clips. In this process, we will store the metadata into our database, and we will upload the cropped clips to our object storage for the future usage. In the next step, it's called packing. So in this step, we are using Ray to empower our packing step. So basically, we select the clips that we want, and then put all the objects, put the clips from the object store and the metadata to a packet file. So this packet file will be used for our training in the last step. So what is the video data packing? Let me demonstrate more. So basically, as I mentioned, video data packing is to store a set of video clips within packet files to facilitate efficient data management and access. The reason why do we need to do this step is also quite clear. Assuming you have tons of small files which are stored in the object storage, the overhead to load all the clips takes lots of time. So in our solution, we just put everything into packet files. And then in the training stage, we will just load this data set directly. So here comes our first solution and first attempt to using Ray data to do it. So you can see in these pipelines, the first step is using Ray data to read from our database, and then do some filterings according to different conditions. And then next, we just repartition our Ray data set into like different blocks for the future parallel processing. The next part is the video processing. So we have 3 key items. The first is download. So we download the data from the object storage, and then we process the videos using the FMPEG. So for example, encode the video into different formats, or decode the videos to get the images from video for the future usage. Lastly, we will just upload the data to the Parquet and then run the training. So for these solutions, we just encounter 2 issues. If you come to the retraining yesterday, you will also feel it. So the first issue is that serialize and deserialize binary object, especially for the large binary objects, takes some time. And another thing is that Ray will spare objects into disk once the object is full. So this one will be a nightmare for us. Assuming all the data will be stored in the disk and you want to read it, it takes lots of time. Based on our first attempt, we figured out maybe it's not a good idea to store video data or like image data in RAID object store, especially in large volume. Then we come up with another solution, so the version 2. How about fuse all the operations into single actor to avoid data transfer between different actors and avoid using the object store? So in this diagram, you can see we have several threads running together. And in each thread, we will download the videos, run some video processing. And the next step, everything will run in streaming, go to the Parquet file. And finally, we just upload it to our database. So this solution works pretty well, and it can achieve high throughput. And also, it is scalable. So for example, if we add more CPU resources, the bandwidth, the whole throughput will also scale up as well. In the last 2 slides, I want to share some lessons we learned and also something that we love about Ray. First thing is about the scalability and the flexibility. I think Xiaohong also mentioned that. We can easily move from like a local Python script to large-scale cluster. We have tried thousands of workers. It works pretty well. Another thing is supports a wide range of workloads. So for example, video, like video decoding, encoding, it supports. For some like deep learning models, Ray also supports. Another thing is about user-friendly. I mean, everybody, I think, in this session are using Python a lot. So Python-friendly is really key for us, and it's quite easy to debug. Lastly, Ray provides unified and user-friendly APIs. So for example, Ray provides RESTful API. So we can integrate its RESTful API into our own platform to monitor the Ray job or submit job. Finally, I just want to share like one tip by using Ray for a while. It's called profiling, and profiling. So profiling and benchmarking, for me, is always the first thing to do. Profiling gives me better understanding of how the system performs, and it could set a baseline for you, especially like in the early stage of the project. In this example, we are using Grafana dashboard to monitor the throughput of our input and output data. By monitoring this dashboard, we can easily know how the system is operating and avoid lots of issues. So for example, out of memory issues, disk spill issues, or even disk fall issues. That's pretty much for my part. Let's hand over to my colleague.
Thank you very much, Xiaohong and Zhibei, for sharing the great insights to the challenge when developing a very robust and scalable audio and video data processing pipeline, and also share how they leverage the capability of Core, data, and reserve to successfully construct efficient data processing pipelines within Bytedance. So next, I'm going to talk about the underlying Ray infrastructures that power a number of use cases, production use cases at scale at Bytedance. So at Bytedance, we are leveraging Ray in multiple use cases, including but not limited to audio-video data processing. We're also using Ray for ILHF with a pretty sizable deployment. We're going to talk about that in another section, another talk, right after this one at 2:30 p.m. By Bytedance researchers. And at Bytedance, we are leveraging Ray's Python native APIs, as Xiaohong and Zhibei mentioned multiple times. And also Ray supports very flexible orchestrations and the scheduling capability of the heterogeneous resources, including various models of GPUs and CPUs, is awesome. We also love Ray's async commutations and its flexible multi-row stack orchestration, which are super desirable to build a large-scale, high-performance AI/ML infrastructure. But like building many other large-scale distributed systems, we also face tremendous challenges, including many production issues when scaling the production workload to thousands of nodes and beyond. And in the next few slides, I'm going to deep dive a little bit. We would like to share what we have learned during this journey and with the broader Ray community. So as you may know, the large language models and many others generative AIs data processing tasks are typical handled offline due to the huge resource demands and tolerance of relatively long processing time. But this is all about cost. But in order to further reduce cost, we use a significant amount of volatile Kubernetes ports to run those data processing tasks. And those Kubernetes ports can be preempted at any time. And Ray worker nodes running on those ports can be added or removed as needed. But at the same time, we also want to ensure that the removal of worker nodes doesn't interrupt the normal execution of any data processing task. And the task should not fail or be interrupted. For example, if a task running on 100 GPUs, for example, and 40 of them are preempted, we expect the remaining 60 GPU to continue operating efficiently with high utilization. So this poses a very significant challenge to us. If you're familiar with the recall does provide a very robust actor and task recovery mechanism. But in the current redata design, when an actor crashes, the system must wait for the actor to restart, and it will stay in pending status until the request resource is supplied. And if the resources are insufficient, then the actor will remain in pending status. So in the next slides, we're going to propose some enhancement to redata to further address those issues. And the first enhancement we propose is task reassignment in redata scheduler. And in simple terms, this means redistributing the tasks of the failed actors in the actor pools to other available actors. And here's a little bit technical detail here. We set the max restart parameters of actor in the actor pool to 0. This means that the redata will fully control the life cycle of an actor. So when an actor crashes, the recall will no longer maintain its life cycle and will no longer attempt to restart the actor. So when the driver detects an actor's abnormal exit, any unfinished task we're going to that previously assigned to the actor are reassigned to other active running actors. And if the redata scheduler will create a new map actors, and if there's no variable resource, the actor will be in a pending status, but this does not block any execution of the redata task. So once a new resources are added, the actor will move to the running state and rejoin the actor pool. The proposed task reassignment is pretty straightforward, but it may introduce new issues. Remember the little technical detail we mentioned in the previous slides? As part of the task reassignment enhancement, we set the max restart parameter to 0. So when an object is lost, we can no longer rely on recourse linkage reconstruction capability to rebuild the object. So, for example, in the diagram on the right, the output of the map operation 1 serves as the input of the map operation 2. If the nodes running map operation 1 crash, the output object is lost. So when a map operation 2 try to read the object, it cannot. It will encounter various of object loss error. So to address this issue, we further propose the second enhancement by asking read data to manage the linkage between the operator input and the operator output, instead of rely on recall to do that. So the read data scheduler, in this case, we're going to introduce a linkage-related data structure. And each operator has a table that records the relation between the input and output data, where the key is the output reference and the input and the value is the input reference. This allows the easy lookup of the input data from the output data. So when the actor pool of the downstream operator, in this case is the map B, encounter an object loss error, it will immediately indicate that the upstream output, map A, has been lost. So the read data scheduler here will use the linkage table to find the input and recompute the output. And there's one trick here. We we set up a cleanup mechanism. So once a block has passed through all the operators and produce an output, the upstream linkage entry will be deleted automatically. Currently, there's one limitation. The solution we propose here so far is supports one-to-one type of operators. But we do believe the all-to-all operator type can be supported as well in the read data. All right, so put it into a broader context. So most read data users work with stable resources, so they may not encounter the issue we just described earlier. However, we believe that this issue is quite universal. Basically, if you're trying to run read data on, for example, any unreliable resources, you're going to hit the same issue. So we believe this enhancement can further provide a higher reliability and stability for read data. Okay, let's put in the technical details aside. Let's enjoy some AIGC music and powered by Ray. And the music is actually generated for Resubmit 2024, and the music generation data is from our data processing pipelines, which are running on Ray. Let's get it started. 1 second. So actually, we have some. I'm going to skip because we are running out of time. So, all right. The Bytedance team here, we deep dive into how to scaling data processing pipelines to petabyte scale, and we believe Ray can provide a great solution to handle large data volumes, optimize the heterogeneous resource allocation, and also provide a flexible orchestration. And we deep dive into the Ray data in infra at Bytedance, how to handle the large-scale offline data processing. We share a journey on running Ray data on unstable Kubernetes ports, and we also propose an enhancement in Ray data scheduler to handle task reassignment and also manage the object linkage. Without further ado, I think thank you very much for your attention, and we would like to take questions. And also one more thing, Bytedance is active hiring here, so we put a lot of QR code. Feel free to scan it. Basically, there are 3 teams here: audio data processing team, video data processing team, and also the tech infra team here in the US. So a lot of opening. Feel free to scan and apply. Thank you very much.
to ask a question, please come to the mic so we can get it on the recording. There's a lot of people, so just queue up there. Thanks.
Hello. So I have one question. So have you thought of like upstreaming this feature to Ray, open source library?
So, that's a good question. Actually, we discussed with the Ray data team at any scale. I think there's a bunch of good things we can follow up. For example, we can define an interface first in the Ray open source upstream, and then probably allow different implementation by different company, for example. And then later on, we probably can further discuss and with any scale team to see if we can contribute back to the upstream. Yeah, so that would be the two steps we're going to take. Thank you.
So another question is regarding the fusion, of operator fusion. So when you do the operator fusion, did you do it at the application code level or like a underlying infra level?
Underlying data.
When you do that, is it more like element-wise operators, or can you also use like aggregation and grouping operators?
Right now, we only support, as mentioned, the limitation, we only support one-to-one operator.
Okay.
But we do believe the all-to operator can be supported among others operators. But yeah, but that's a good one.
Okay.
Yeah.
Thank you.
Thank you.
Hello, great talks. So I have a question related to when you mentioned that your cluster is going to scale to, like, for example, thousands of nodes, right? Have you encountered anything related to GCS, the scalability and stability issues that, the GCS constantly drop off and things like that? And how do you deal with that?
Yeah, global schedule. Have you heard this? Looks like our client, which is the data and the audio and video data processing, they haven't hit that issue yet.
Okay, all right, thank you.
Hi. So related scalability question. So you run jobs with thousands of nodes on Kubernetes infrastructure. How do you address the scalability challenges of Kubernetes itself?
So yeah, that one we are building Ray on top of Kubernetes, as shared previously, right? So far, I think the Kubernetes, the document limitation is about 15K nodes, right? So I think so far we haven't hit that limit yet. That's what I can share so far.
Makes sense. And one more question. So the Ray head node is also running in a Kubernetes pod that's inherently volatile. So how do you think about fault tolerance of the whole system or failures of the head node?
Can you repeat that question one more?
Yeah. How do you think about potential failures of the Ray head pod?
We are, I think, as far as I know, it will rely on Ray's HA ability a lot at this time. Yeah, and also Kubernetes HA. Yeah.
Makes sense. Thanks.
Hello, great presentation. I have a question regarding scalability as well. So not everyone has the luxury to have 1,000 nodes in a single place. Have you guys ever thought about deploying Ray on multiple clusters? Is this something you have tried?
You want to take this one, Zhibei? Or Xiaohong? Yeah.
Yeah, so first I'm the user of the Ray, and our Ray data infra team, they will set the Ray across the different clusters, but each cluster is running separately.
Yes.
Does this answer your question? Yeah.
Yes, but is there any coordination between clusters you guys have encountered, or is it probably fine because you're just sharding the data properly?
So each cluster is running separately, so there's no communication between them.
I see. Does it ever come to you there is a communication need, or that's not a usual case?
So far so good, because basically we just split our data into different parts and send the data to each cluster to process it. Yeah.
Gotcha. Thank you.
Thank you. Yeah.